Here's our basic refrigeration system, and we're going to look at each of these components in detail. We're going to start with a simple circuit and build up. Essentially, we have refrigerant which runs through our system. This is the medium we use. Our refrigerant has unique properties. We'll talk a bit more about those, but essentially it can exist in two states, as a liquid or a gas. Our compressor discharges high pressure gas. We pass it through a heat exchanger, and we go from here through this valve here. This is called a thermal expansion valve, which restricts the flow, and then we pass it through another heat exchanger. Now this is where our refrigeration space is, and from here they say we essentially remove heat from the space. So we start with warm products in our refrigeration space, and heat is absorbed from our warm products into our refrigerant, and then it passes through here, and we remove that heat through another heat exchanger called the condenser. So they liken it to taking a sponge, absorbing heat, and then taking that heat and wringing it out. So we remove heat from here, from our refrigeration space, and we remove it over here. So we'll have a look at how each of those components work. The main part of our componentry is our compressor, and with our refrigeration system we're pumping refrigerant. As I said, we'll talk a bit more about refrigerant, but we discharge, and whenever we compress anything it has to be as a gas. So we have a high temperature gas refrigerant which discharges from our compressor. From there we go through a heat exchanger. So the high temperature gas passes through a heat exchanger that we generally, on a vessel, will pump seawater in and out, and this changes the temperature of our high temperature gas, and what that does is cause it to change state. So from this is called a condenser. It cools the refrigerant, and as it does, it turns from a gas into a liquid. Now it's still a fairly high temperature liquid, but due to the unique properties of our refrigerant, it causes it to change state. Okay, from there we go through, we call the thermal expansion valve, or TX valve. Thermal expansion. This is basically a restriction in our system, and as you could think of it as an orifice. As we restrict the flow of liquid through our valve, our restriction valve, what happens is it becomes a cool liquid. So we get this cold, low pressure liquid. Then we come through our evaporator. Now this is another heat exchanger. Where we run our, now it's a cold liquid refrigerant which runs through our evaporator. We put a fan in front of that, and we can circulate air, and what that does, any warmer parts within the refrigeration space absorb heat into our cold liquid, our liquid refrigerant, and then as it's absorbing heat through our evaporator, it starts warming. What we want is for this finally to have warmed up enough that it turns back from a liquid into a gas, and we have a low pressure gas, and this returns back to the suction side of the compressor. So I'll just review that cycle again. Our refrigerant, we have our compressor, is compressed as a gas. It becomes a high temperature gas, and we pass that through a heat exchanger. We call that the condenser. Generally we use seawater to pass around our refrigerant gas, and what this does, as we absorb or remove heat from the refrigerant, it changes state into a liquid. We pass it from there down to the thermal expansion valve. We restrict the flow, and as it restricts the flow through this valve, it changes state into a cold liquid. And from there we pass our cold liquid through our evaporator. It absorbs heat from in and around the refrigeration space, gets our refrigeration products nice and cool, and as it does, it starts to warm up the refrigerant liquid in the evaporator, turns back to a gas, and this passes back to the suction side of the compressor. Now we basically, if I bring a dotted line right the way through the middle of my compressor, and then I'm going to bring another dotted line through the middle of my evaporator and condenser, what we have on this side is my high pressure side, and anything after the TX valve is my low pressure side. And if I look from halfway through between the evaporator and the condenser, up the top here, up in this top half, is my gas side. You can see we got gas here, and down the bottom here, from anywhere from here down through from my condenser round to my evaporator, is my liquid side. So we have the high pressure side on this side, our low pressure side on this side of the compressor. We have our gas side up the top here, and my liquid side down the bottom. Alright, so we're going to have a look at some other components and how this sort of fits together. So what we're planning on doing here is we've started our basic system. We're just going to add some components as we go. So I'm just going to review what we covered then. We had our compressor. It discharges our high pressure, high temperature gas, our refrigerant gas. We take that high temperature gas, high pressure gas, pass it through a heat exchanger, which, as I said, was normally seawater, and this is called the condenser. And what that does is remove heat from our high temperature gas, and it changes state to a liquid. And from there we pass it through our thermal expansion valve, or TX valve, and this is a restriction. And as we restrict the flow of liquid through here, it becomes a cold liquid, and this is what we use to do work. We pass this cold liquid through another heat exchanger, and this is called our evaporator. This is inside our refrigeration space. This absorbs heat from our refrigeration system, and absorbs heat and warms up, becomes a gas again, and then discharges back to our compressor. So we're just going to add on the TX valve here. There's a way that this regulates. It opens and closes as well as restricting, and what it does, it measures the outlet of the evaporator. It has a sensing bulb, and this is used as, it's a liquid filled bulb which is sensing the temperature, and this uses capillary action through a tiny little tube which comes down to the TX valve and applies a pressure to open and close to regulate the position of the valve, more open or more closed. And this is really the brains behind the operation of our refrigeration system. So what happens is when we open up our refrigeration space door and we stick a 6-pack of warm beer in there, what that does is essentially make the space warm, and our compressor fires up and starts circulating through the condenser, and we end up with this cold liquid. Now, as it's coming through here, this is fairly warm, so it causes this valve to open fully, and we get a lot of flow of liquid refrigerant through here to cool down our space. Now, we might have a beer fridge that is intended to operate about 4 degrees Celsius, +4, and this becomes quite warm when we've filled it up with warm products, and as a result this might go up to say 8 degrees, in which case this valve will be fully open. We're getting a lot of liquid refrigerant flow through our evaporator, and then as the heat is absorbed from the products through the evaporator, then our space starts coming down in temperature. And at that point, when we start getting close to 4 degrees, this valve starts restricting. Now what that does is restrict the flow of liquid through here, and we end up with this large cooling effect, and this is starting to get colder and colder, and this is restricting. Next, we're going to add some controls for our compressor. What we have first up is a pressure switch. This is called a low pressure cutout, and then on this side we have high pressure cutout. So this is the low pressure, the suction side of our compressor. This is the discharge side, so this is the high pressure. Low pressure cutout, high pressure cutout. Alright, now this one will cut the compressor out in the event of an emergency, so if anything goes wrong with the system, to protect the compressor, it will cut out. This guy does the normal day-to-day operation of stopping, and we'll see, and starting the compressor. But it's a low pressure cutout switch that when the pressure in here reduces and reduces on the suction side of the compressor, it hits a point at which the suction pressure is sufficiently low and it will stop the compressor from operating. Now, it works on this in conjunction with, or in tandem with, the TX valve. So as we said before, when our refrigeration space starts getting colder and colder, it's close to the temperature that we want our beer in our fridge, then the sensing bulb on the TX valve will be cold, and that will be restricting the flow of refrigerant through the TX valve. So this valve all but closes. So what we have is the compressor still running, and it's trying to suck against a valve that's closed, and so this keeps drawing down. The suction pressure keeps getting lower and lower to a point where it hits a pressure switch, a setting on the LP cutout, and stops the compressor. That's all well and good. Our products in our fridge, our beer starts to get warm over time, and this temperature from 4 degrees starts creeping up and up, and we get up to 6 degrees, at which point because our sensing bulb is starting to get warmer, it starts opening up our TX valve a little bit. Now, we've already got pressure on this side from our compressor. As soon as that valve starts opening a little bit, we start getting a bit of refrigerant flow through our TX valve, which starts coming up and operating on our evaporator. As soon as this occurs, the pressure switch on here starts increasing. So on our LP side, we have a cutout pressure. We've also got what they call a differential, pressure differential. There's two settings. There's one, if we think about this as high and low pressure, and we have a low pressure setting here, And then they have a differential, which is an amount by which another setting is above this. And this is the low pressure cutout, and this is the differential. It's the amount that's above the low pressure cutout, and they call that the differential. And this is what starts the compressor. So as soon as it reaches the differential, then the compressor starts. So you can call that the cutout and the cut in, basically. It's both on the low pressure side, but this is what controls the start and stop of the compressor, but it does it in conjunction with the TX valve, because the TX valve starts restricting as the space becomes down to temperature, starts restricting until we get full suction on the suction side of the compressor. It hits the low pressure and cuts out the compressor. When the space starts warming up, the sensing bulb warms up, opens up the flow through the TX valve, and the pressure starts increasing, hits the differential and starts the compressor. So this guy cycles the compressor on and off. As I said, we're going to build and expand on our system, so I'm going to sketch it up, and then I want you to practice doing this before we add other components. So we had our compressor, discharge from here through our condenser, and then we came down to our TX valve, thermal expansion valve, went through to our evaporator, and back to the suction side of our compressor. And we said this was a heat exchanger, our condenser, and our evaporator. And this was our thermal expansion valve. And we had a sensing bulb on the outlet. Of our evaporator, and this sensed the temperature within the evaporator and regulated the TX valve. And then the compressor itself was controlled by the low pressure cutout and the differential, and then we had our safety, which was the HP cutout. So I have a go at sketching up that system. And before we add some more components, I want you to be comfortable with drawing this system. In fact, what we can do, just to make it look a little bit neater, is to draw our sensing bulb. We can draw that as a dotted line. And that just indicates that it's a small line. As we said, it's a capillary tube which operates, opens and closes, regulates the flow through our TX valve. Okay, so we're going to just do a bit of a review. You should have practiced sketching this out. So I'm just going to run through it and see what you remember. So compressor, what discharge from the compressor? It has to be a gas. So it is a high pressure and of course high temperature gas. And we had a switch here. What was this one called? That's right, the high pressure cutout switch. From there we went down to this. What was the name of this? Yes, indeed it was the condenser, and which is a heat exchanger. We use seawater to pass through a heat exchanger, reduce the heat, and it changes state into a liquid. That's right, and from here we're still on the high pressure side, and then we bring it to a valve. What was this called? The thermal expansion valve, or TX valve, and that restrict the flow of refrigerant. When we did that, the unique properties of our refrigerant cause it to change temperature. As it restricts, it becomes low pressure. So we had the high pressure side on here. After the TX valve, it becomes low pressure. So it was low pressure, low temperature liquid, and we passed that through our heat exchanger, the evaporator, which drew heat out of the system, and as it did so it warmed up and became a gas again, which passed back to the suction side of the compressor. And we had our LP cutout with the differential which stopped and started the compressor. You can think of it as an LP, low pressure, cut out, cut in and cut out. And then we had the sensing bulb, which is sensing the temperature on the outlet of the evaporator, and which is regulating the flow through the TX valve. Good. All right, we're going to add a few more bits. First thing we need is what we call an oil separator. So this, we get some carryover from the refrigerant, and from here we have a separator to return the oil back down to the sump of the compressor. Now you will get some small amount of carryover through the system. It's able to manage with that, but the majority of oil is separated from the refrigerant and sent back to lubricate where it's supposed to be. Now on smaller systems, this is all sealed and contained. They call it hermetically sealed, and which means it has the electric motor and all the compressor, oil return, all of that sort of stuff all in one. So here's our oil separator. Oil separator. After the condenser, we have what we call the liquid receiver, and this is basically a reservoir. It's like a tank or a cylinder that holds a level of refrigerant in the system, and basically this allows us to have extra volume of refrigerant in the system, just to supplement, and so it's a reservoir on standby. After the liquid receiver, we have what we call a filter dryer. Now this is like a canister. They're kind of replaceable, they're not easy to replace, but our filter dryer contains desiccant beads, just like we have in those moisture absorbing sachets that you get in food packets to keep moisture out of, and these absorb any of the moisture that's in the refrigerant, which tends to upset our system. I'll talk more about moisture in the system later. After that, we've got another guy which is called a sight glass. Now this enables us to get a visual, a view basically of what is happening in the refrigerant. It serves two functions. It's sort of like a clear window, and around the outside, or sometimes in the middle, we can have a bullseye, but we've got a moisture indicator which changes colour. So normally it's green, and if we get moisture in the system, it'll turn red. But we've also got this clear glass, and that should have refrigerant liquid going through it, so we shouldn't really see any gas. Gas tends to move through as bubbles through the sight glass, so we should just have, and we will get that when the compressor first starts up, but after a while it should settle down and we should just get liquid passing through the sight glass. So that's an indicator. So here we have our same schematic system. Let's run through this. We've got a refrigerant. We're going to talk a bit more about those, but this one is using refrigerant R134A, and this has a discharge and a suction pressure. So when it discharges from the compressor, as we said, we get a high pressure gas or vapor in this, it's called here 600 kPa, so that's about 6 bar. And so when it comes out, it discharges at 6 bar, and it'll be at around 60 degrees Celsius. We come through our condenser and we cool that high temperature, high pressure gas, and when we cool it, it obviously cools it from around 60 degrees down to about 15 degrees Celsius. It's still at the same pressure. So remember before we said this side is the high pressure side. So we're at 6 bar, 600 kPa. We've just cooled it down to 15 degrees. When we do that, the refrigerant changes state. We go from a gas, this was the gas side, remember? As we cool it, it changes from a gas down to a liquid. We're still on high pressure. And then we put it through the TX valve. When we restrict it, it reduces the pressure. So we go from 600 kPa down to 50 kPa, about half a bar pressure. And what this does is significantly drop the temperature of that liquid. So we've gone from about 15 degrees Celsius on this side to about minus 15, 16 degrees Celsius on this side. So now we have a low temperature, low pressure liquid. And we go from here through the evaporator and with our cold liquid, and as it comes out it starts warming, and we're still on the low suction side. It's still at that around half a bar pressure, but it's warmed up, and this is significant enough to, when it warms up, it starts to boil off and become a gas again. And this is what we want. We need a gas to come back into the compressor because we know we cannot compress a liquid. So this is just for this. This is the typical operating pressures and temperatures you might see on an R143A system. Okay, we're at this level, MED1, you won't be required to memorize what are particular pressure ranges or temperature ranges for a refrigerant, but it's helpful to understand that process of, that pressure and temperature relationship at each of the phases in our system. We're just going to have a quick look at some of the componentry that we saw in the system, and we'll look at it in a bit more detail. So here's our compressor, two different types here. They're both hermetically sealed, which is they're sealed from escape of the refrigerant gas, and it has all the compressor contained within this system, and we've just got an inlet and a discharge, and inside of here are the motor starter controls, the electric motor and the compressor, all fully sealed. It's got little mounts here. We have oil in here to lubricate the compressor, but in this type of system normally you don't find a sight glass or anything to check on the oil level. This one is for a larger system that is controlled by a three-phase electric motor. Again, it's hermetically sealed. It's all completely sealed, and we just have the suction and discharge up here in the cylinder head. And this one has a oil reservoir here with a sight glass that we would check before starting the system. Here we have two different types of condensers. Our condenser again being the heat exchanger, which pulls heat out of our refrigerant gas, and here's one type that has tubes with cooling fins and has air passing past the condenser, and here's our shell and tube heat exchanger. As a condenser, uses seawater passing through the middle, and then our refrigerant passing around through baffles around the tubes. Our liquid receiver, as we said, this is to allow for a greater amount of refrigerant in the system. It's basically a reservoir of refrigerant, and fairly simple. Here's our filter dryer. These are a replaceable item. They will absorb moisture. As I said, they've got desiccant gel beads inside of them to pull moisture out of the refrigerant, and they are replaceable, but we'll talk a bit more about servicing, because it can only be done by a suitably qualified refrigerant mechanic. Here's our sight glass. As we said, these are used in line in the system after the condenser. In our liquid, these are in the liquid line on the high pressure side, and we should see no air bubbles. We normally get air bubbles at the start when the compressor first starts up, but after a while that should settle down as we get a steady stream of liquid through the sight glass. And we have a moisture indicator, which can be in the center or around the outside, and in this particular one it's dry if it's green, and if it turns this brown color, then it's got moisture in it. Our thermostatic expansion valve, as we said, is a restriction in the system, and our liquid refrigerant comes in one side through the valve in here and out the other, and this is regulated via this valve here, which opens and closes to restrict or open that orifice through there, and it's controlled by the sensing bulb, which is on the outlet of the evaporator, has a capillary tube all the way down through here acting on the top of that valve. Our evaporator is located inside the refrigeration space and has a fan or fans which blow air past the evaporator tubes, and as we stated, it absorbs heat energy from inside the space and passes it in through the cool liquid going through the evaporator tubes. You'll notice that on most refrigeration systems, when we open the refrigerator, then it stops the fans, because what that does is prevent a circulation of air from outside that has moisture in it from collecting onto the evaporator tubes. So most systems will operate like that. So refrigerants are products that have a unique relationship between temperature and pressure, and they also change states from a gas to a liquid. There's a lot of different refrigerants about, and they're all prefixed with the letter R. So the most commonly used refrigerant used to be R12. It's a freon gas, and which is a HCFC, a hydrochlorofluorocarbon. Okay, there are other types of freons which are fluorocarbons or hydrofluorocarbons. All of these products are what we call ozone depleting. So if they're released into the atmosphere, then they can destroy the ozone layer. Okay, so R22 was commonly used after R12. It's still in use, but is being phased out. And there's a lot of other refrigerant gases. We have R502, R717, which is ammonia, R134A, which is a blend of refrigerants, R404A, and R115. So many different refrigerants, and you can look at your own MSDS for whatever refrigerant you've got, but it's safe to assume that our refrigerants are toxic, and if you were to have them released into a large quantity into a small space, then you would have to consider this a confined space and act accordingly to isolate, evacuate, and to gas free the space. What is certain is that as to operate with refrigerants, you need to be a licensed refrigeration mechanic, and to handle refrigerants and its systems. So basically we are left as operators, so we can operate the equipment, but we can't do any major servicing. So we'll talk a little bit more about that in a little while. There is one thing that we are able to do if we do get into trouble and we want to avoid releasing our refrigerant gases, and that's called a pump down if our system allows for it. So we'll talk about that and what that entails. But the other point with refrigerants are that they're very expensive. So we want to, as well as being environmentally damaging and potentially toxic, we want to try and reduce and limit any leaks of our refrigerants. Okay, now we're going to introduce into our system solenoids. So I'm pretty sure you've covered these already, but just in case, so a solenoid, we have an iron core, wrap a coil around it, apply a charge to it, and the coil will tend to move and centralize itself. So we can do a lot of things with a solenoid and use it as electrical switches, they're commonly used, or we can use a solenoid to open and close valves, that sort of thing, directional control valves for our steering. Alright, so that's our solenoid. How are we going to use this into a refrigeration system? You should be well used to drawing this system by now. I'm going to sketch it up and we'll draw it and include a solenoid. I'll show you where that goes. Oh. So from a compressor, cutout, high pressure cutout switch, we had our condenser, our accumulator or our liquid receiver, filter dryer, sight glass, and our TX valve, thermal expansion valve, and through our evaporator and back with our LP cutout. Okay, so we can also, our controlling is done via our TX valve and using the LP cutout, and we also have one more valve on the system, or we may have another valve on the system, and that's this guy here, and this is our solenoid. A solenoid is able to control the starting and stopping of our compressor, and it works with a controller. It has a temperature sensor inside the refrigeration space, and then it has another controller. I'm not going to draw all of that in, but it'll control between a temperature range that's inside the refrigeration space. So if we wanted, say, plus 4 degrees Celsius in our fridge space, then it would turn on and off the solenoid control valve at a range around that 4 degrees Celsius, so that if the valve is closed, then it would draw down on the suction side until the LP pressure switch turned the compressor off, and then as soon as the temperature gets warmed up a bit more, then a controller turns the solenoid or activates the solenoid, opens the valve, and the pressure on the high side starts flowing through. The pressure builds up on the low pressure side and the compressor starts again. So it works in conjunction with the TX valve, because the TX valve is still going to regulate. It's going to open and close a little bit, you know, in accordance with the temperature that's in the evaporator. But we also have the additional controls, or we may have with a solenoid, that can basically, this valve just opens or closes. It's just completely open or completely closed, as opposed to our TX, which is regulating. Now this is particularly useful when we have more than one refrigeration space. So if we had a combination of a fridge and a freezer. So we're going to have a look at that system and how that might look. But so far you should be pretty savvy at drawing up this complete system, and we're going to have a look at a 2-room fridge system and sketch that up and see what that looks like. So now I'm going to draw you a 2-room fridge system. So I'm going to have a second refrigeration space with a condenser in it, an evaporator in it. And what we have to do here is add another solenoid valve and another TX valve. I have my sensing bulb here and my TX. Now I've left off the sight glass and filter dry and all that sort of stuff, just kept it simple. But you can see now we've got 2 separate circuits, one supplying my fridge space, and this one might be at 4 degrees Celsius, and this might be my freezer room at say minus 18 degrees C. And what we have here is we've got a TX valve that's rated to control around that temperature, and this one's rated at that temperature rating +4. And then we've got a controller which controls both of these solenoids to, I've represented a dotted line as an electrical, that's a controller. And our control is going to regulate, it's also taking a temperature sensor in each of these refrigeration spaces, and then it's just opening and closing this to maintain that temperature range in both of these fridges. Alright, the other thing we need when we've got a 2-room fridge system is to have a back pressure regulating valve. Now we can have one on each outlet of the evaporator, but in a 2-room fridge system we can get away with just having one. Basically what we want to do is to be able to regulate, to throttle in this valve after the evaporator on the warmer refrigeration space, because we're going to get less throughput with our warmer space than our cooler space. We regulate this just to get the right flow rate between the 2 fridges. So this is called a back pressure valve. Okay, so you need to be able to sketch this system in M&E1. You need to understand it. You also need to include the other things that I didn't put in here, you know, like the LP cut in, LP cut in, cut out, HP cut out, our filter dryer, receiver. As we stated, you need a refrigeration handling license in order to do servicing work on a refrigeration system. But if we do end up with a leak, as we said, our refrigerant in our system is very expensive and it's also environmentally damaging. So one thing we are able to do is to do what we call a pump down if we get a leak. So if we get a leak in the system, one way we can find a leak, sometimes you can hear a discharge of refrigerant. We can sometimes visually see it. But if it's a very small leak, what we can do is take a container and just put some detergent in it, put some water in, and then we get a paintbrush and dip that in and then paint all the way around the pipework, and wherever we get a leak, wherever the detergent is, it'll start bubbling and show us where the leak is. And if it's going to be some time before we're able to get back into port and get our system repaired, we can do what we call a pump down. So what this involves is on the outlet of our receiver, on most industrial systems will have a valve. We can close that valve, start the system and pump the liquid down into the liquid receiver. It'll cut out on low pressure cutout. We can wait 10 seconds, restart the compressor, and we might be able to pump down a little bit more. It'll stop again within a matter of seconds. Do that a few times, and then we can close the inlet valve to the receiver, and we've contained most of the refrigerant into the receiver. The only difficulty with the only problems with this is that we've now rendered our refrigeration system ineffectual. It's not going to operate, but what we have done is saved most of our refrigerant. Okay, now we also need to be aware of some of the faults that we can have on a refrigeration system. But what I'm going to get you to do is have a look in your learner's guides, and I want you to have a look at some of the faults we're going to be talking about and looking at this system in much more detail when we do the pracs